Hello and welcome everyone. Thank you for joining us for our expert sessions. These short webinars take place every week and last no more than 30 minutes, bringing you valuable insights from industry experts. Today's session will be presented by Sunny Solanki. He's a senior technical manager at I-Gard. Sunny is an electrical engineer from McMaster University with 8 years of experience in protection systems and relays. Throughout his career, he has educated consultants and end users on the benefit of integrating electrical protection products into their designs to enhance the personal and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high resistance grounded systems, low resistance grounded systems, hybrid HRG systems, ground fault and arc protection systems, resistor-based solution, and personal protection products. We are excited to have him here today, and we appreciate your participation. Without further delay, I would now request Sunny to take over from here.
Thank you, Devansh. Today's topic is going to be on the Canadian Electrical Code 2024 requirements for impedance monitoring and 48-hour fault isolation. So we're just going to go through resistance grounded systems. Resistance grounding involves adding impedance between the transformer neutral and ground to limit the ground fault current. And this limitation prevents the buildup of sufficient energy for arcing, thereby fostering a safer operational environment. So when we have a ground fault on one of the phases to ground, this resistor is essentially in series with the ground return path, and that's how we can limit the fault current to a specific value. Now in the IEEE standards, the reasons for limiting the current by resistance grounding may be one or more of the following. It's mostly to reduce the electrical and mechanical stresses from high levels of fault current, reducing electrical shock hazards, and to reduce the probability of arc blast or flash hazards to personnel, as well as equipment, and reducing the momentary line voltage dip occasioned by the occurrence and clearing of a ground fault. We're also trying to control the transient overvoltage by sizing this resistor in accordance to the charging current of the system. And in doing so, this type of resistance grounded system is much safer than an ungrounded system, which could experience transients in its ground return path. Now in NFPA 70E, which is a standard for electrical safety in the workplace, in Annex O.2.2, it says that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, and enabling achievement of an electrically safe work condition. Further to this, in Annex O.2.3, they list out 9 different incident energy reduction methods. Of the 9 listed, high resistance grounding is the only one that's reducing the likelihood of exposure. By placing that resistor from neutral to ground, you are basically allowing that resistor to be in place when the first fault comes into the system. All the other incident energy reduction methods are acting after the fact that the arc is already in the system and it's looking to reduce the magnitude. So this could be like zone selective interlocking, differential relaying, arc flash mitigation systems with fiber optic sensors. But with high resistance grounding, we're taking care of 95% of the cases being phase to ground failures, which will limit fault current to 10 amps or less on a system that's 5 kV or less, and leave insufficient fault energy and thereby help reduce the arc flash hazard level. The only issue with high resistance grounding is that it will not affect arc flash energy for line to line or line to line to line arcs. In this case, that means a phase to phase or a 3-phase failure. And that's because the current would just circulate between the 2 phases and not go back to the source to be limited by the neutral grounding resistor. So high resistance grounding is really good for phase to ground failures, but it can't do anything on phase to phase or 3-phase failures. Luckily, majority or 95% of the cases of insulation failure or electrical failure is in relation to a phase to ground failure. Now, if we look at the National Electrical Code in 250.36, it allows impedance grounding systems to be used as long as line to neutral loads are not served. And basically, the grounding impedance is selected to limit fault current to a value that is slightly greater than or equal to the capacitive charging current. Therefore, any ground fault that results is not going to cause transient overvoltages in the system because we're sizing in accordance to the charging current. And that will allow you to continue operating until you have a downtime where you can address the phase to ground fault that's existing in your system. Now, in the Canadian Electrical Code in Section 10, Grounding and Bonding, in -300, they have clauses for impedance grounding systems. And it says that the integrity of an impedance grounding system shall be monitored and controlled as required by Table 17. And we have to continue signaling until the condition is corrected. In 2021, they released Table 17 on the right-hand side. And Table 17 is very useful for consultants and end users to determine the conditions in which they need to initiate an alarm or de-energize their system. So if we look at the columns here, this is the ground fault column. This is the short circuit condition. And this is the open circuit condition of the NGR. So the short circuit condition of the NGR makes the system solidly grounded. The open circuit condition makes the system ungrounded. And ground faults in the system are just to understand that there's a ground fault being picked up, and that's usually picked up with elevation in neutral voltage, as well as current flowing through the neutral. On the left-hand side here, you have impedance grounded system configurations. On the first row, it says line to neutral loads are served. I highly recommend that you just delete this row from your mind completely, because it's not recommended to distribute a neutral in a resistance grounded system. And each of the three cases indicate that you have to alarm and de-energize the system immediately. In row number 2, it talks about systems that are three-phase 3-wire at 5 kV or less, and ground fault is limited to 10 amps or less. In this case, in the event of a ground fault condition, you alarm and de-energize the system within the time rating of the impedance grounding device. But if the impedance grounding device is continuous rated, then you only have to alarm the condition of the ground fault without having to trip the system. Now, when we get to systems that are greater than 5 kV, or when ground fault is limited to something greater than 10 amps, then we alarm and de-energize the system within the lesser of 48 hours or the time rating of the impedance grounding device. But if I look at the circulating wattage on these systems that are greater than 5 kV versus a low voltage system, it may be hard to hold the fault for 48 hours. So for example, if I have a 600 volt system with a 10 amp NGR, my circulating wattage is about 3,470 watts. So that's just taking the line to neutral voltage of the system and multiplying by 10 amps. Now, in a 13.8 kV system with a 10 amp NGR, that would equate to 80 kilowatts circulating for 48 hours, which is likely not possible. So most consultants and end users choose to trip with time coordination with respect to their feeders and their subfeeds, and just try and make sure that they can get the most uptime by just isolating the feeder that is experiencing the fault. When it comes to the short circuit and open circuit cases, for short circuit, it says to alarm and de-energize the system within 48 hours. So this is where we implemented a delay in our relays to allow for 48 hours to be implemented as a delay. And we also give you a pre-warning that the timer has started so that you're aware that this fault is in the system and you have up to 48 hours to clear it. When it comes to the open circuit condition, we either alarm if we can still detect a ground fault in an ungrounded system, and if we can't detect a ground fault in an ungrounded system, we alarm and de-energize the system within 48 hours. And this is true for both of the rows. Now, for resistor monitoring, we have the Sigma 3C, and it combines ground fault protection and resistor path fault monitoring to safeguard systems from ground faults and open or short circuits in the neutral grounding resistor and its connecting conductor. So in the past, we used to use the term NGR fault, but now we're looking at the entire path from the XO point to ground. And if you look at the Canadian Electrical Code in figure 10-B12 or B10-12, I forgot which one, it says that we have to monitor right from the XO point to the ground. So that means that we have to make two connections to our XO point. One is for our sensing resistor, and one is for our NGR. Now, because there's a requirement to detect open and short circuit conditions even when there's 0 volts and 0 amps at the neutral, we had to implement an injection method. And that injection method takes the path up through the sensing resistor to the XO point. And once it reaches the XO point, majority of the signal chooses the path through the NGR. We're using a high frequency signal because when our signal reaches the XO point, it'll see these inductances as a higher impedance than the NGR itself, so that majority of our current will flow through the NGR and experience that voltage drop as it comes back to our relay to be analyzed. In addition to that, the sensing resistor also gives us a reference for neutral voltage, and our CT is also giving us a reference for neutral current so that we can also pick up ground fault conditions. Now it's designed for systems ranging from 480 volts to 69 kV. We can monitor resistances as low as 6 ohms, and we're compatible with HRG systems up to 5 kV, as well as LRG systems beyond 5 kV with currents ranging from 1 amp all the way to 1,000 amps in both configurations. Now in the past, and also in the US, because they don't have an open and short circuit requirement for monitoring the resistor, they would typically utilize a ground fault relay with a CT connected at the neutral to examine how much current is flowing through the NGR so that they can pick up their ground faults. But in the case of an open circuit condition here, this CT is essentially blind to the fact that they've just lost their system ground, and this entire system is now floating. This will impact your protection schemes downstream that may not work with an ungrounded system. And alternatively, if we have a short circuit condition, this CT may be bypassed, and we're no longer reducing the probability of an arc flash incident anymore because now our system is solidly grounded. So with that being said, with this implementation of the sensing resistor as well, we can now detect open and short circuit conditions, even with 0 volts and 0 amps on the neutral. And we are meeting the code requirement with the Sigma 3C relay. So when we talk about table 17, we look at row 2 as high resistance grounding, where the system voltage is below 5 kV and fault current is less than or equal to 10 amps. So high resistance grounding's main benefit is to maintain operation during a single phase to ground fault while satisfying arc flash mitigation as per NFPA 70E and CSA Z462. When it comes to low resistance grounding depicted as the third row in this table, low resistance grounding is more important for reducing the energy available for a phase to ground fault to a specific value. So rather than having kiloamps of ground fault current, we're limiting to a value somewhere between 25 to 400 amps, and then allowing our ground fault pickup schemes downstream to be more sensitive to ground faults, and thereby creating a bit of a safer environment. Even though these are at hundreds of amps, it's better than having thousands of amps, I would say. Now, when we have a short circuit condition and we are not experiencing any current or voltage at the neutral, our high frequency signal comes along the path to the XO point and it goes down the shorted path to ground. So it doesn't experience the voltage drop across the resistor, and we get the full signal back to our relay. So when we get the full signal back without experiencing the voltage drop across the resistor, we can deduce that we're in a short circuit condition. When there's a loss of continuity, so our high frequency signal is shown there. If we get an open circuit here and we don't receive our signal back, then the relay has a counter inside and it just gives it some time, and then it indicates that there's an open circuit if it never gets the signal back. Now, a lot of customers have YYPTs where the primary is grounded. And our signal is not impacted by YYPTs where the primary is grounded. PTs in general have a very high impedance when it comes to AC signals. When it comes to DC resistance though, these types of PTs have a lower resistance. So comparable is, I guess, the AC resistance would be in the mega ohm. But in the case of a DC resistance, it could be in the range of ohmic value between 100 to 300 ohms, or even less than that. It depends on the manufacturer. But that's why we chose the high frequency signal. So some of our competitors are using a DC-based injection. When their DC-based injection reaches the XO point, it sees the inductances as short circuits and leaks out into the system, finding this alternative path to ground. And because the DC resistance of these PTs is very low, it's going to see this alternative path and falsely confirm that it's checked the NGR when it has not. Now, another mode of our relay is measurement mode, where if we have a neutral voltage and a neutral current, we back calculate the resistance using Ohm's law and compare it to the resistance nameplate on the nameplate. If it's within the band of 66% to 150%, we're still in the clear, but anything beyond the boundaries in the red zone is considered an NGR fault. So as mentioned, the high frequency injection mode is a 4 kilohertz signal. And when the signal reaches the XO point of the transformer, most of the signal flows through the NGR path, as the impedance of the phase inductances are much higher than the NGR resistance. And with the CT monitoring that we've also placed inside of this relay, we can detect if the current transformer is open or shorted, and it provides an alarm to alert users to any issues with the CT as well. So here's a case study from an automotive manufacturing facility in Ontario. So an automotive parts manufacturing plant in Ontario operates with the HRG system. And because of the new code requirements, they wanted to upgrade their electrical safety infrastructure to comply with the continuous impedance monitoring and 48-hour fault isolation. So to comply with the 2024 electric code, they updated their resistor monitoring and installed a Sigma 3C, which has the 48-hour delay for resistor fault. They integrated systems with the existing HRG infrastructure and trained staff and updated fault response protocols. That way they can go out and look for the NGR faults and provide corrective action for it during a downtime. So that reduced their unnecessary downtimes, and it allowed them to have an early detection of the NGR degradation so that they have room of 48 hours to resolve it. Obviously, they were reducing arc flash risks and improving operational efficiency and reduced downtime. So now they're in full compliance with CEC 2024, and adopting the new CEC requirements enhance their safety, reliability, and also regulatory compliance. In addition to that, that 48-hour delay gave them a bit of time before they had to shut down the system. So back when resistor monitoring was introduced in 2018 Canadian Electrical Code, you had to trip the system basically right away on resistor fault. So with the new code requirement, we're seeing that they're allowing for 48-hour delay. So that is the presentation, and we're going to head over to the questions pane so that I can provide some answers. Hi, what about HV substations? Which CEC table should use as reference? So you're still going to be using table 17. It depends on how high of a voltage you're talking about, but typically HRG is used in the range of low voltage all the way up to like 69 kV. In the case of a 13.8 kV system, you're going to be using row 3 on table 17, and you would most likely be going with a low resistance grounded system, limiting fault current between 25 to 400 amps, and using a time rated resistor since you're tripping on first fault. So typically 95% of our low resistance grounded quotes are either 10-second, and then the remaining percentage is either 60-second or 1 minute, or sorry, 10-minute. In this case, if you have a generator whose wind down time is longer than 10 seconds, that's when you would need the 60-second rating. And if you have a generator whose wind down time is longer than 60-second, you may need to go to the extended or a 10-minute rating. Any recommendation for PT vector group where neutral resistance is used for both less than 5 kV or more than 5 kV systems? We have applications where we've done resistance grounding for systems that are lower than 5 kV and also systems that are greater than 5 kV. We completed a few jobs just recently at 25 kV as well as at 13.8 kV. And our most popular product is a 600 volt cabinet, which includes the resistor and monitoring device at 600 volts and 480 volts. So we're comfortable in both. One thing to look out for, Pradeep, is to basically determine if your neutral is being distributed or not. An ideal candidate for resistance grounded system would be a 3-phase 3-wire system, and a system in which there isn't any other solid ground connection between the conductors and ground. So if you're looking for a retrofit application, just contact me at the email here, and I can help you out on that point. Yeah, so for 13.8 kV, Miriam, yeah, it's likely you're going to be using low resistance grounding between 25 to 400 amps, either 10-second or 60-second. And I can also help you on that if you contact me via email. Do we need to use open delta? You could use open delta if you wanted to. It's an alternative method of limiting fault current by placing PTs in a certain configuration from the phases. We also have broken delta options, and we design those as well. But if there is a neutral available in your system and you can access it, then I feel like the resistor is gonna be doing the same function. And you also can monitor the resistor for open and short circuit. On an open delta, it's probably a bit more difficult because now there's more components to monitor for. You have the PTs that you're going to be using, and then also you're going to have the resistor, which is on the secondary, to limit whatever's happening on the primary. So it's on a case-by-case basis. We can offer both. We can offer open delta, broken delta. We can offer NGRs in both high resistance grounding and low resistance grounding configurations. So let us know how we can help you on that front. And thank you for coming out to this presentation. It looks like the questions are done. So I think the next step here is we're going to have another session next week on Tuesday. So stay tuned for that and make sure you sign up, and we'll see you then. Thank you very much for your time. Take care.